Yes, it is possible to feed a two-family service with a specific configuration. This setup includes a 200 amp meter pan, 2-inch PVC conduit, and 3/0 THHN copper feeders. The National Electrical Code, or NEC, mandates a minimum of 3/0 THHN copper feeders for a 200 amp service. The conduit must be sized appropriately based on the number and size of the conductors used. In this scenario, a 2-inch PVC conduit is suitable. The meter pan must be rated for the maximum amperage of the service. To calculate the ampacity of the feeders, use the following formula: ampacity equals conductor rating times correction factor. For 3/0 THHN copper, the conductor rating is 200 amps. The correction factor, considering 75% fill in the conduit, is 0.8. Therefore, the calculated ampacity is 200 amps times 0.8, which equals 160 amps. The ampacity of the feeders must adequately carry the maximum load for both the first and second floors. The maximum load for a 200 amp service is 160 amps, calculated as 80% of 200 amps. Consequently, the 3/0 THHN copper feeders are adequately sized for this application. Based on this information, it is feasible to feed a two-family service consisting of a 200 amp main circuit breaker panel for the first floor and a 100 amp main circuit breaker panel for the second floor, utilizing a standard 200 amp meter pan and 3/0 THHN copper feeders run in 2-inch PVC conduit. The NEC provides comprehensive guidelines for electrical installations, ensuring safety and proper functioning. Firstly, you must adhere to the NEC requirements for conductor sizing. This involves selecting the appropriate size of conductors, such as the 3/0 THHN copper feeders, based on the ampacity requirements of the service. Secondly, conduit sizing is crucial. The 2-inch PVC conduit specified is suitable for housing the conductors, but it's essential to ensure that the conduit fill does not exceed the NEC limitations. Overfilling a conduit can lead to overheating and potential fire hazards. Thirdly, the meter pan must be properly rated for the service's maximum amperage. In this case, a 200 amp meter pan is suitable since it matches the service's rating. The ampacity calculation is vital for determining the allowable current carrying capacity of the conductors. The formula, ampacity equals conductor rating times correction factor, helps account for dirting factors such as conduit fill. In this scenario, the 0.8 correction factor accounts for the 75% fill in the conduit. Feeder sizing is another essential consideration. The feeders must be sized to handle the maximum load for both the first and second floors. In this example, the 3/0 THHN copper feeders are adequately sized since their ampacity is sufficient to carry the maximum load for the 200 amp service. Let's delve deeper into the NEC requirements for service conductors. According to NEC Table 310.15b16, 3/0 THHN copper conductors have an ampacity of 200 amps when installed in a raceway or cable. This ampacity is based on an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature exceeds this value, a correction factor must be applied to direct the conductor's ampacity. The NEC provides tables for temperature correction factors in Article 310. The NEC also specifies requirements for conductor insulation types. THHN insulation is a common choice for service conductors due to its high temperature rating and resistance to moisture and chemicals. However, it's essential to verify that the insulation is suitable for the specific environmental conditions of the installation. Conduit fill is another critical factor to consider. The NEC limits the percentage of conduit cross-sectional area that can be occupied by conductors. These limitations are specified in Chapter 9, Table 1 of the NEC. Exceeding the conduit fill limits can lead to overheating and difficulty in pulling conductors through the conduit. The 2-inch PVC conduit specified in this example is suitable for housing the 3/0 THHN copper conductors, provided that the conduit fill does not exceed the NEC limitations. The meter pan must be listed and labeled for its intended use. Listing and labeling indicate that the meter pan has been tested and certified by a recognized testing laboratory such as Underwriters Laboratories or UL. The meter pan must also be rated for the maximum voltage and amperage of the service. Grounding and bonding are essential safety measures for electrical systems. The NEC requires that all metallic enclosures, such as meter pans and service panels, be properly grounded and bonded to ensure a low impedance path for fault currents. Grounding and bonding help to protect against electric shock and equipment damage. Overcurrent protection is another critical safety feature. The service panel must be equipped with overcurrent protection devices, such as circuit breakers or fuses, to protect against overloads and short circuits. The overcurrent protection devices must be properly sized to match the ampacity of the service conductors. The NEC provides guidelines for selecting the appropriate overcurrent protection devices in Article 240. Working space around electrical equipment is also essential for safety. The NEC requires that adequate working space be provided around electrical equipment to allow for safe access and maintenance. The working space must be clear of obstructions and must meet minimum dimensions specified in the NEC. Voltage drop is another factor to consider when sizing service conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the conductors. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Coordination of overcurrent protection devices is essential for ensuring selective tripping. Selective tripping means that only the overcurrent protection device closest to the fault will trip, minimizing the impact on the rest of the electrical system. The NEC provides guidelines for coordinating overcurrent protection devices in Article 240. Short circuit current rating, or SCCR, is another important consideration for electrical equipment. The SCCR of equipment must be sufficient to withstand the maximum available short circuit current at the point of installation. Equipment with an insufficient SCCR can fail catastrophically during a short circuit event. The NEC requires that electrical equipment be marked with its SCCR. Arc flash hazard analysis is a critical safety assessment for electrical systems. Arc flash is a dangerous electrical explosion that can occur when there is a fault in the electrical system. Arc flash hazard analysis helps to identify potential arc flash hazards and determine the appropriate personal protective equipment, or PPE, required to protect workers. The NEC requires that arc flash hazard analysis be performed for certain electrical equipment. Surge protection is another important consideration for electrical systems. Surges are transient overvoltage events that can damage or destroy electronic equipment. Surge protection devices, or SPDs, can help to protect against surges by diverting excess voltage to ground. The NEC recommends the use of SPD in certain applications. Power quality is another factor to consider for electrical systems. Power quality refers to the characteristics of the electrical power supply, such as voltage stability, frequency stability, and harmonic distortion. Poor power quality can cause equipment to malfunction or operate inefficiently. The NEC provides guidelines for power quality in Article 110. Energy efficiency is an increasingly important consideration for electrical systems. Energy-efficient equipment and practices can help to reduce energy consumption and lower utility bills. The NEC encourages the use of energy-efficient equipment and practices in various articles. Renewable energy sources, such as solar and wind power, are becoming increasingly popular. The NEC provides guidelines for the installation of renewable energy systems in Article 690. Standby power systems, such as generators and uninterruptible power supplies, or UPSs, are used to provide backup power in the event of a power outage. The NEC provides guidelines for the installation of standby power systems in Article 700. Fire alarm systems are critical for life safety in buildings. The NEC provides guidelines for the installation of fire alarm systems in Article 760. Communication systems, such as telephone, data, and cable TV, are essential for modern buildings. The NEC provides guidelines for the installation of communication systems in Chapter 8. Low-voltage systems, such as lighting and control systems, are used in a variety of applications. The NEC provides guidelines for the installation of low-voltage systems in Chapter 7. Special occupancies such as healthcare facilities, hazardous locations, and swimming pools have unique electrical requirements. The NEC provides guidelines for these special occupancies in Chapter 5. Electrical plan review is an important step in ensuring the safety and compliance of electrical installations. The electrical plan should be reviewed by a qualified electrical engineer or inspector to verify that they meet the requirements of the NEC and other applicable codes. Electrical inspections are conducted by electrical inspectors to verify that electrical installations are installed in accordance with the NEC and other applicable codes. Electrical inspectors have the authority to approve or reject electrical installations. Electrical permits are required for many types of electrical work. The electrical permits help to ensure that electrical work is performed safely and in accordance with the NEC and other applicable codes. Electrical contractors are responsible for performing electrical work in a safe and workmanlike manner. The electrical contractors must be licensed and insured to perform electrical work. Electrical apprentices are individuals who are learning the electrical trade under the supervision of a licensed electrician. Electrical apprentices must complete a prescribed training program to become licensed electricians. Continuing education is essential for electricians to stay up to date on the latest changes to the NEC and other electrical codes. Continuing education courses are offered by various organizations such as trade schools, community colleges, and professional associations. Electrical safety is paramount. Electricians must follow safe work practices to protect themselves and others from electrical hazards. Safe work practices include wearing appropriate personal protective equipment, using insulated tools, and de-energizing equipment before working on it. Lockout/tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. Lockout/tagout procedures involve disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. Arc flash safety is a critical concern for electricians. Electricians must be aware of the arc flash hazard and take steps to protect themselves from arc flash injuries. These steps include wearing appropriate personal protective equipment such as arc-rated clothing, gloves, and face shields. Electrical troubleshooting is a skill that electricians must possess to diagnose and repair electrical problems. Electrical troubleshooting involves using various test instruments such as multimeters and clamp-on ammeters to identify the source of the problem. Electrical maintenance is essential for ensuring the reliable operation of electrical equipment. Electrical maintenance includes inspecting equipment for signs of wear and tear, cleaning equipment, and tightening connections. Power factor correction is used to improve the efficiency of electrical systems. Power factor is a measure of how effectively electrical power is being used. A low power factor can lead to increased energy consumption and higher utility bills. Power factor correction involves adding capacitors to the electrical system to improve the power factor. Harmonic mitigation is used to reduce harmonic distortion in electrical systems. Harmonics are unwanted frequencies that can cause equipment to malfunction or operate inefficiently. Harmonic mitigation involves using filters or other devices to reduce harmonic distortion. Ground fault protection is used to protect against ground faults, which are unintentional electrical connections between a live conductor and ground. Ground fault protection devices, such as ground fault circuit interrupters, or GFCIs, are designed to detect ground faults and quickly disconnect the power to prevent electric shock. Surge protection is used to protect against voltage surges, which are transient overvoltage events that can damage or destroy electronic equipment. Surge protection devices are designed to divert excess voltage to ground, protecting sensitive electronic equipment. Uninterruptible power supplies are used to provide backup power in the event of a power outage. UPS are commonly used to protect critical equipment, such as computers and servers, from data loss or damage due to power outages. Emergency lighting is required in many buildings to provide illumination in the event of a power outage. Emergency lighting systems must be designed to provide sufficient illumination to allow occupants to safely evacuate the building. Fire alarm systems are used to detect fires and alert occupants to evacuate the building. Fire alarm systems must be designed to meet the requirements of the NEC and other applicable codes. Communication systems are used to transmit and receive information. Communication systems include telephone, data, and cable TV systems. Low-voltage systems are used in a variety of applications, such as lighting, control, and signaling systems. Low-voltage systems must be installed in accordance with the requirements of the NEC. Special occupancies, such as healthcare facilities, hazardous locations, and swimming pools, have unique electrical requirements. These special requirements are designed to protect occupants from electrical hazards. Electrical safety training is essential for all electricians. Electrical safety training should cover topics such as safe work practices, lockout/tagout procedures, arc flash safety, and electrical troubleshooting. The NEC is a comprehensive set of rules and regulations for electrical installations. The NEC is updated every 3 years to reflect the latest advances in electrical technology and safety practices. It is important for electricians to stay up to date on the latest changes to the NEC to ensure that their work is safe and compliant. The NEC is not a design manual. It provides minimum requirements for electrical installations. Electrical engineers and designers must use their professional judgment to design electrical systems that meet the specific needs of the application. The NEC is a living document. It is constantly being revised and updated to reflect the latest advances in electrical technology and safety practices. It is important for electricians to stay informed about these changes to ensure that their work is safe and compliant.